Hey, Algebra, we are identifying and graphing linear functions, which is going to require us to be able to describe their characteristics. Let's jump into it. So if you were in class, I didn't actually have us do this assignment or example, whatever, but imagine that you had a rope and you measured it and it had a certain length, let's say 10 inches, and then you were to tie a knot in that rope. Well, then all of a sudden that rope would now be like, let's say 7 inches long, and then you tie another knot in that rope and now it's like 4 inches long, and then 1 inch long, and then eventually it's just this mangled up mess of rope, right? Well, here's what's going on. We could graph that scenario, and that what we would find out is it would be like this. It would be like this, and then this, and then this, and then that's the idea. And if you're like, that's interesting that he would say it's like that. Well, the reason I was so precise in what I said is right here, we said that's going up one, right? And then over here, this is going down three, down three, down three, right? Well, we are describing a slope, okay? And slopes are something you have on a, guess what? A linear function, okay? That's something you already knew, but this is just a little bit of a visualization of what would happen. And what I did do in class is I grabbed my lanyard, the thing you hang around your neck, and there's the ID on it, and I said, okay, let me hold it out to my arm, and so here's a fake arm. You could tell it's fake by how good it looks, right? And what I did is I actually tied a knot in it, and we clearly saw that the next time I held it out, it was shorter, right? And so that was, again, the idea. That was our rate of change. And if you're like, wait, this just says identifying, hang on. Rate of change. A linear function, let me zoom out, a linear function has a constant rate of change. This is something I want you to put into your brains. A linear function has a constant rate of change, also known as a slope, okay? And this right here is our basic equation for a linear function. And you might know that, in fact, I know you know this. This is called the slope intercept form. And one thing I mentioned in class is this is like we have perfected the linear function. This is the most basic linear function. In fact, we call this one like the parent function. And it's like we're in the business of making linear functions. And if you're like, what's a linear function even? He keeps saying it. It's this. There's a line. That red line is a linear function. The blue lines are the x-axis and y-axis. Welcome to math class. Okay. So if we have perfected this, that means we can change a number here and a number here, and we can basically get any looking line you can think of. It can be short, it can be really tall like that, it can be really wide like that, it can be a negative slope, a positive slope, a zero slope, etc., right? So a linear function has a constant rate of change. A non-linear function does not have a constant rate of change, and we're going to look at that. Oh, and also a non-linear function is not a line. Okay, cool. So over here, this guy is a non-linear function because it doesn't have a constant rate of change. Now, we could kind of argue about that if you want to. You could say, well, wait a second. What if you went from here to here? Isn't that a constant rate of change? Sure, maybe we could argue that, but then what about from here to here? Is that the same rate of change? First of all, that already started a curve, so that really is kind of thrown out. But I mean, clearly, like if I could pick this line up, I probably could, and draw it over here, it would look like that. That means these two slopes are different, and therefore it does not have a constant rate of change, right? So over here, this guy has a constant rate of change. It's up one over that much, up one over that much again, up one over that much again. In fact, I'm saying over that much because I don't really know, but even still, as long as I hit like that boundary of that grid line, you can kind of see I pretty much drew the same stair steps. So, linear, nonlinear, moving on. Here's a different visualizing of it. We kind of did it right here, but let's take a look at this. Does this represent a linear function or a nonlinear function? Well, if you'd like to guess, if you'd like to figure it out, pause the video. Otherwise, here we go. Notice that the x goes up 3 and 3 and 3. 3, 6, 9, 12, right? And the y goes up, or goes down 6, down 6, down 6, down 6. We can write that this has a rate of change of -6 over 3. Now, here's where it's like a little bit of a spoiler alert. You know that slope is rise over run. I know you guys know it. If you're randomly a math person here, you might not know that because you're not in my class. But we've talked about it a lot already. Rise is the change in y. Run is the change in x. So look, that's changing by 3. This is changing by 6. There we go. So yes, this one is a linear function. This one, on the other hand, is not. This rate of change is not constant, okay? What's happening is right here it's 7 over 2.5, but right here it's 11 over 2.5, and then 15 over 2.5, and those are clearly different rates of change. So now we did this in class also. We decided, hey, let's figure out which one of these are linear or not. So if you want to, pause it. Here we go. I'm going to tell you yes, no, 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 yes, no. Now let me tell you why. So first of all, I'm going to try to graph these a little bit. This first one right here, y equals 3.8. There's 1, 2, 3, 4. This line right here is y equals 3.8. That is a function. That is a linear function. It's a straight line. That's about it, okay? This one is not a function. It looks about like that. I don't know how it interacts with this line. I'm not like graphing it for perfection right now, but it's definitely a curve, right? Not linear. This one is exponential. It looks like this. Definitely not linear, right? This next one right here, 2 over x, is going to kind of look like this. I didn't make that perfect, but it is very clearly not linear. This one right here is super linear. In fact, if you distribute that 6, not only is it linear, that's slope-intercept form. Y equals mx plus b, where our slope is 6. Our y-intercept is -6. We could easily graph that. And then last but not least is this guy right here, x squared minus y equals 0. If we were to rearrange this, it would be y equals x squared, and that is a parabola. So that blue line that I just drew right here, definitely not a linear function. So in summary, we have here, let me write it out. 1, 2, 3, 4, 5 ways of describing a linear function, okay? So let's go through this. We have an output is 3 more than the input. That feels a little strange to say. It definitely doesn't make me think of a straight line, but it is, okay? And that's one interesting thing about this is the way we can communicate, the way it can be interpreted is going to show different things. Like, for instance, when I look at that, I know exactly what that looks like, but you might think, I don't know it looks like that or not. You know what I mean? These don't make me immediately think of this, but that's just me. You know, I don't know exactly until I do a little bit of calculations. And it's like, what do you mean? Well, like this. The x is going up 1, up 1, up 1. And this is going up 1, up 1, up 1. Okay, so then the slope is 1 over 1. And right here, that slope is 1. In fact, I don't see that. Y equals mx plus b. That's slope-intercept form. That's our slope. The number in front of x. And you're like, there isn't anything in front of x. Sure there is. We have 1x, don't we? And then also, I can look right here and go, hey, there's the y-intercept. And in fact, what's a y-intercept? It's that. And it's also that. And if you didn't see that, it was right there. Okay. And then the same information that's here is here. This is just called a mapping. Oh, there it is, mapping. And then this is obviously an equation and a graph. There you go. Do these represent linear or nonlinear functions? This one's definitely linear. It's a line, okay? This one is not linear because it's not just a line. See, as I'm drawing my line, it went that way, so not a line, okay? Not linear. Is this one linear? Well, x is going up 1, up 1, up 1. Y is going up 2, up 2, up 2. Yeah, this is actually y equals 2x plus 3. How do I know that? My slope is rise 2, run 1 because of this. My y-intercept is 3 because of this. When x is 0, that's when you get the y-intercept, whenever x is 0, okay? Over here, this is one we debated about a little bit in class. This is not linear, because how do you get from here to here? Well, you divide by 2. Actually, no, you multiply by 2, because 1/16 times 2 is 1/8, and then 1/8 times 2 is 1/4. So what this one looks like, and I drew this in class, so I'm going to take the time to draw it now, is I did a really, like a tall y and a not super long x. So this is 1, 2, 3, 4. This is 1. So halfway is going to be 1/2. And if we cut that, that's 3/4. And if we cut that, that's 1/4. If you cut that, that's 1/8. If you cut that, that's 1/16. And if you're thinking, why is he doing this? Well, because 1 is at 1/16, right? And 2 is at 1/8. And 3 is at 1/4. And 4 is at 1/2. Does that look like a straight line to you? Well, I don't think so, because check this out. If I were to just connect even those two dots with as straight a line as I can draw, I mean, it's clearly not going through the other dots. This is not linear. It's a curve like that. So this one, I was going to put an X on it, not linear. Okay. Over here, linear functions, their solutions, x, y. They're two variables, okay? X, y are on a coordinate plane that represents all the solutions. Sometimes they're distinct, sometimes they're connected. Speaking of that, here's the difference. Discrete is those distinct answers. And so an example they give is like the integers from 1 to 4, which would look like this. 1, 2, 3, 4, 5. Those are the integers from 1 to 5. Now a continuous domain is, what did it say? They're connected. So that's all the numbers from 1 to 5. And if you're like, well, this is all the numbers from 1 to 5. No. There's 1, and then there's 1/2, and 1/4, and 1/8, and 1/16, right? Those are all of the numbers from 1 to 5, right? We could go infinitely small. We could be like 1/1,000,000th, right? That is a number between 1 and 5. Sorry, 1 and 1,000,000th. There you go. So back to what the heck are we supposed to learn here? Discrete is like just dots on a graph. So here's a 2D version. Just dots on the graph. I don't care if you think, well, that could be a line. No, that's not what we're getting at here. We're just talking about this one would have a discrete domain, but okay, well, now let's throw on a line. That red line has a continuous domain because it's clearly a straight line, right? They're all connected. So really, that's kind of where we left off. There were a couple real-world examples we could do, but we cut it off there so we could get some practice in. I think you guys are really well-versed in identifying and graphing linear functions, describing their characteristics. Let me know what questions you got. See ya.